Okay, so we finished up 2.1a yesterday, and now we're moving on to 2.1b. And we're going to talk about another way to calculate a limit. So far, we've been making tables to calculate limits. So in other words, we've been making a t-chart, putting a bunch of x's in that are close to the number, seeing what they're close to. And that's certainly the most pure way to calculate a limit. It's the definition of what a limit is. It's the meaning behind a limit. But it would be nice to have other methods for calculating limits. And so there's going to actually be a lot of ways to calculate limits. And today we're going to talk about the second way, which is called using limit laws. So for limit laws, if you have two functions, let's call one of them f and one of them g, and those two functions are being added together to make another function called f plus g. And if you're calculating the limit as x approaches a number of that f plus g, it turns out that you can either calculate the limit of f plus g, or you can calculate the limit of f and then separately calculate the limit of g and then add those answers together. So over here, you're adding the functions together to create a new function, and you're calculating the limit of that new function, as opposed to over here, you're calculating the limit of the first function and the limit of the second function and then adding later. So here you're adding first and then limiting, and here you're limiting first and then adding the answers. It turns out that you can do this either way, and you'll always get the same answer. So I'm going to put an equal sign in between there. And the same thing works with subtraction. Hey, how's it going?
How are you?
Just fine. So you can, in a sense, distribute a limit past plus and a limit past subtraction, and either way you get the same answer. There's also a limit law for multiplication. So if you have two functions multiplied together and then you take the limit, you can take the limit of the first function and the limit of the second function and then multiply those answers together. So in my mind, this is kind of like distributing limit. The limit goes past the plus and past the minus and past the multiplication. Okay, the same thing works with division, but with division it doesn't always work. With addition and subtraction and multiplication, it always works like this. So I'm going to write down, so we'll call this limit law 1 and this one limit law 2. So here's the third limit law, the limit law that involves division. And this works. So here division is happening first and then you're limiting later. And it turns out that you can limit first, so limit of the top thing and limit of the bottom thing, and then divide later. But this one doesn't always work. This one doesn't work. So this is true, this equals is true, unless the limit as x approaches a of g is equal to 0. And this doesn't work in this case for obvious reasons, because if this limit is 0, then you're dividing by 0. And the thing that throws students off is they think, okay, well, since you're dividing by 0 over here, that means the limit doesn't exist. And that's just not true. Just because you get a 0 down here, it could be that this limit exists anyway. So that's probably going to throw you off. Okay, so just to emphasize that even further, if you use limit laws, and get 0 over 0, it is not necessarily true that the limit does not exist. In other words, the limit might exist. So what's going on is, if you get this 0 over 0, this means that you're not allowed to use, that this here is not a legal use of the limit laws. And so you'd have to try something else. And so far, the only other thing we have to try is a table. So at this point, if you use limit laws and you get 0 on the bottom, you're going to have to make a table to figure out the limit, because the limit laws are not working. So limit laws are really useful. They work a lot of the time. They always work with plus and minus and multiplication. And a lot of times they work with division. But sometimes this fails and you have to try something else. This 0 over 0 is called an indeterminate form. And indeterminate means it cannot be determined. So what I'm saying is that if you get 0 over 0, you don't know what the answer is. It's not determinable, or you cannot figure out what the answer is based on this. It would be tempting to say that the limit doesn't exist. But in fact, you know nothing when you get this. You have to make a table or try another method that we'll learn in the future. But at this point, you'd have to make a table. Okay, so we're going to calculate a limit here. We're going to calculate the limit as x approaches negative a half of 3x squared times 2x minus 1. And it would be totally fine to make a table to calculate this limit. That's what we did in 2.1a. And I think it would work in this case. But since we just learned limit laws, let's practice using our limit laws on this question. Okay, so right here is a multiplication sign. So we have the limit of two functions multiplied together. So what that means is that you can take the limit of the first thing and then multiply that by the limit of the second thing. So I'm using limit law 2 over here, the limit. I'm distributing the limit past this multiplication sign. Okay, then there's another multiplication sign here, so I'm going to distribute the limit past that multiplication sign. And there's a subtraction sign here, so I'm going to distribute the limit past that subtraction sign. So now I'm going to have the limit as x approaches negative a half of 3 times the limit as x approaches negative a half of x squared. And then all of that, because that's this, right, is multiplied by the limit as x approaches negative a half of 2x minus the limit as x approaches negative a half of 1. Okay, so in this first step from here to here, I just used the multiplication limit law. And then from here to here, I used the multiplication limit law and the subtraction limit law. Okay, there is another limit law that involves powers. So let me come back here and write that one down. It turns out that if you have the limit as x approaches a of a function to a power, so here you're powering first and then taking the limit, it turns out that you could take the limit first and then do the power second, and you'll get the same answer. So it's just switching the order. Here it's power first and then limiting second. Here it's limiting first and then powering second. So I'm going to apply that limit law right here. I'm taking the limit of something squared. So limit law 4 says that I'm allowed to take the limit of the something and then square that instead. And I'm going to just recopy this limit as x approaches negative a half of 3. Okay, then finally I'm going to distribute this limit past this multiplication sign. So I've got the limit as x approaches negative a half of 2 times the limit as x approaches negative a half of x minus the limit as x approaches negative a half of 1. Okay, so to get from here to here, just used a bunch of limit laws. Okay, so now I've boiled it down to some limits that are pretty easy to calculate. So the first thing I'm going to look at here is the limit of 3. So this is a function, kind of. It's a function, it's the function 3. And what this function outputs is 3 no matter what. So I can make a quick table for this. So I got to pick stuff close to negative a half, right? So negative 4.49 and negative 0.499. And this function here always spits out 3. So when I punch in negative 0.49, it spits out 3. When I punch in negative 0.499, it spits out 3. What are these getting close to? They're getting close to 3. And I could pick numbers above negative a half, but they would be 3 also, right? So these are getting close to 3. So the answer to this limit is 3. Okay, and for the same reason, this function here always spits out 2. So the limit there is going to be 2. So let me leave a space here, times blank squared. And then times, talked about this limit coming out to 2. Okay, now let's look at this limit so we can fill in this blank here. So this is the function y equals x. So let me make a quick table for that one. I should pick numbers on both sides of 0.5, but I know it comes out the same on both sides of 0.5. So this function is the function y equals x, so what that means is it always spits out what you plug into it, because the y is always equal to the x. So if you plug in negative 0.51, it spits out negative 0.51. And if you plug in negative 0.501, it spits out negative 0.501. So if these numbers are getting close to negative a half, the y's are going to be getting close to negative a half as well. And so the limit is negative a half. That same exact limit is shown here. So that's negative a half again. And this function here spits out 1 no matter what you plug in. So if you plug in numbers close to negative a half, it's going to spit out 1 in the y column. And those are getting close to 1. So that limit down there is 1. So now we just have to do this math. Let's see, negative a half squared is 1/4. 2 times negative a half is negative 1. Negative 1 minus 1 is negative 2. So I've got negative 6/4. So the final answer is negative 3/2. Okay, so it turns out that this limit, the limit of this function, is negative a half. And the method we used to calculate it was the limit law method. Could have made a table just straight from here. could have plugged in numbers close to negative a half into this function, and those numbers would have been getting close to negative 3/2. And in fact, on this problem, might have been easier to do it that way. It probably would have been less of a pain than writing all this stuff out. But the limit laws are important for other reasons rather than just calculating limits, and so we need to understand and know how limits work. The fact that limit distributes past plus and distributes past times and subtraction and usually division. Okay, next problem is example 3. I'm going to calculate the limit as x approaches 1 of x squared plus 3x minus 4 all over x minus 1. Okay, so since we're working on limit laws, let's try using the limit laws. Here we have a division, and there's a limit law that I just erased that says usually you can take the limit of the top thing and then the limit of the bottom thing and then divide later. So I just switched the order. That's what limit laws do. They say, and here it was dividing first and then limiting, and I'm using a limit law to try to take the limit first and then divide second. Okay, then I'm going to use a bunch of other limit laws. On the bottom, I'm going to distribute the limit past this minus, and I'm going to distribute the limit past this plus and this minus. And then I'm going to put the limit inside this square, and I'm going to put the limit past that times. So I'm going to do all those things in the same step. The limit inside this square here, and the limit past this plus, and then also past this multiplication sign, and past this minus. I know it's a pain to write all this down, but showing work is a big deal to me, so please do that on the homework as well. It'll help you learn the laws. We're not just trying to get the answer here. We're also trying to have a clear understanding of what the laws say. Okay, so now I've boiled it down to this. And we've got the limit as x approaches 1 of x. So let's make a table in our head. This is the function y equals x, right? So whatever I put in, it spits out. So if x is 7, then the y is 7, because it's y equals x. So if x is 0.9, it spits out 0.9. If x is 0.99, it spits out 0.99. So the y's are getting close to 1 when the x's get close to 1. So this limit is 1. So I've got 1 squared plus. Okay, now this function always spits out 3. So when I plug in 0.9, it spits out 3. When I plug in 0.99, it spits out 3. So those are getting close to 3. Here we're back to the function y equals x. 0.9 spits out 0.9. 0.99 spits out 0.9, so that's getting close to 1. Here it's the function y equals 4, so 0.9 spits out 4. 0.99 spits out 4, so the limit's 4. Here the limit's 1. We've seen that a couple times in this problem. And here the limit is 1. So figuring out the top, it's 1 plus 3 minus 4, which is 0, and 1 minus 1, which is 0. And here's where it's tempting to say, oh, I'm dividing by 0, therefore this limit doesn't exist. And that's just plain not true. This is an indeterminate form. What that means is this step right here wasn't a legal step because we're only allowed to distribute limit past divide if it doesn't come out to 0 on the bottom. But since it did come out to 0 on the bottom, that means this step right here was not a legal step. So unfortunately, all this that we wrote down doesn't tell us anything. It's good to have it down. It's part of your work. But our method failed. So what that means is we have to make a table. Because we only have 2 methods so far. All right, so we're going to just go ahead and plug in 0.9 and 0.99 and 1.1 and 1.01 into this function and see what they're getting close to. Go get my calculator. Okay, so don't forget parentheses, 0.9 squared plus 3 times 0.9 minus 4 divided by 0.9 minus 1 is 4.9. And then 0.99 comes out to 4.99. Now I'm plugging in 1.01. That comes out to 5.01. And now 1.1. Bet it's going to be 5.1. Let's see what happens. So it turns out that these numbers are getting close to 5. So this limit is 5. That's the correct answer. Certainly would have thought, based on this, that the limit didn't exist. But that's just not true. Turns out the limit's 5. So limit laws are good. They work a lot of the time. But sometimes they don't work. And the limit law actually told us when it wasn't going to work. Doesn't work if the limit on the bottom comes out to 0. Okay, that brings us to example 4. I wasn't holding this. I don't know if you got all that in the table a second ago. Okay, so now we're going to try the limit as x goes to 0 of sine of x over x. And we could try limit laws on this one. Take the limit of the top and the limit of the bottom. But the limit on the bottom would come out to 0. So that means limit laws don't work. So we're going to have to make a table. So we're going to plug in 0.1 and 0.01 and negative 0.1 and negative 0.01 into our function sine of x divided by x. And I've actually typed this in some other years, and 0.1 spits out 0.99833, and 0.01 spits out 0.99998, and this spits out 0.99998 and 0.99833. So these are getting close to 1. So this limit is 1. Final answer is 1. So this limit here is a very famous limit, and so I want to make sure that you know what this limit is. So I'm going to make an emphasis to write this down. So this is a fact that you need to have memorized. The limit as x approaches 0 of sine of x over x is equal to 1. And I should point out that if you're having trouble getting these answers, you might not be in radian mode. In calculus class, you have to always be in radian mode. Can't tell you why right now, but I will tell you why later when you know a little bit more and can't, understand the explanation. Just know that in calc class, you have to be in radian mode. So yes, if you're not getting these numbers, change to radian mode and then you will get these numbers. So this limit is 1, for sure. That's a fact that you need to have memorized. So for the next problem, we're going to use that fact. We're going to calculate the limit as x goes to 0 of x plus sine of x over x. Okay, so I'm going to start out by doing some algebra. When you have a plus sign, you can distribute division past plus. So you can rewrite this as x divided by x plus sine of x divided by x. And I'm taking the limit of that. And then x divided by x is 1. So this is 1 plus the sine of x over x. Calculating the limit as x goes to 0 of that. And then limit can distribute past plus. So I'm going to take the limit of 1 plus the limit of the sine of x over x. And then this is easy, this limit, because when x is 0.1, this function spits out 1. When x is 0.01, this function spits out 1. So this limit is 1. And this limit is easy as well, because this is the one we have memorized. And so the final answer to this limit is 2. Okay, so at this point, we are generating a list of ways to calculate limits. And right now we have 3 possible ways. First way is make a table. Second way is use limit laws. And third way is use the fact that the limit as x approaches 0 of sine of x over x is 1. And we're going to add to this list, we're going to add one more thing to the list today. But before we get to that, we're going to calculate a couple more limits using tables. So we're going to calculate the limit as x approaches 1 of this. And I want to point out that there's a couple of ways to write this function. This is kind of a weird looking function here. This is kind of a weird looking function. Another way to write it is int x. So this and int x are the exact same thing. So this is the same problem written down in two different ways. And what int x, that's what you would type in your calculator, this is called the round down function. So what it means is, if you input a number into this function,
Sponsors, please come to the main office. Samantha Forrest, Kylie Africa. Please come to the main office.
so if you input a number into this function, you round down no matter what. So if you plug 7.8 into this function, the output would be 7, because 7.8 rounded down is 7. If you inputted 7.1 into this function, the output would be 7. Okay, so we're going to make a table to calculate this limit. And we've got to pick numbers that are close to 1. So we're going to go 0.9 and 0.99 and 1.1 and 1.01. Let's start here because it's a little bit easier. 1.1 rounded down is 1. 1.01 rounded down is 1. But 0.9 rounded down is 0. It's kind of weird. It's not rounding. Remember I said 7.8 rounded down was 7. So 0.9 rounded down is 0. 0.99 rounded down would be 0. So these numbers are getting close to 0. These numbers are getting close to 1. So the limit does not exist. And the reason why it doesn't exist is because the limit from the left side is 0 and the limit from the right side is 1. Okay, the last thing we need to look at today, and then we're going to do one problem using this, is a theorem called the Sandwich Theorem. Sometimes it's called the Squeeze Theorem. And the way theorems go is they have an if part and a then part. And if this stuff happens, then you get this for free. This happens automatically.
Good afternoon, London High School Department Chair meeting. We will be meeting in the main conference room in about 10 minutes. Come on down.
Okay, so what's going to happen with the sandwich theorem is we're going to have our function that we really care about, and it's called f of x in this theorem. And then there's going to be a second function that it's always smaller than. So the function we care about is always smaller than another function, and it's always bigger than a third function. So what we're going to do is we're going to get our function that we care about trapped in between two other functions. And then we're not going to calculate the limit of the one we care about. We're going to calculate the limit of the smaller one and also calculate the limit of the bigger one. And it turns out that if these two limits are equal, then you get something for free. So two requirements for the sandwich theorem. First of all, you got to trap your function in between two other functions. And then you have to verify that this limit is the same as that limit. And if those two things are verified, if they're true, then something magical happens. I'll tell you what the magic is in a second, but let me draw you a picture so we can kind of see what the magic should be. Okay, so here's your function f of x, the one you care about. And let's say that g of x is always above this function, as the theorem requires. And let's say that h of x is always below the function. And then you're getting close to this number a. Well, if h of x is getting close to the same thing that g is, then of course f has to be getting close to that same thing. So here's the scenario. You're on the highway, you're in the right lane, and there's a semi in the left lane, and you're coming up to an exit ramp, and there's a semi coming on the ramp. Sorry, not an exit ramp, an entrance ramp. So you're f of x, you're the car in the right lane, and let's say the semi is getting closer and closer to your lane, and then the semi in the left lane decides to switch lanes and gets closer and closer to your same place, then you're going to get trapped in the middle. That's what's going on in here. If you're always in between two semis, and this semi is getting close to the same place as this semi, then you're going to get squeezed in the middle. You're going to get sandwiched. So then the magic that happens is the limit as x approaches a of f of x is also equal to what these limits are equal to. So let me call this limit L. So these limits are equal, and whatever that limit is, maybe it's 7. L is 7 then. And so then what's going to happen is that limit will also be L. Okay, so we've got our ways to calculate limits over here. The fourth way is to use the Sandwich Theorem. Okay, so we're going to use that theorem to calculate this limit. Keep writing a instead of 0. I apologize, I don't know if I'm running out of time,
Samantha Morse, please come to the main office.
because I don't know when this bell ends, because I'm not even taping this during a bell. So it could be I'm getting towards the end, and if there's 2 minutes left afterwards, you can watch the rest on Google Classroom, or at this point you have enough information to probably get through the homework as well. Okay, so we're going to calculate this limit using the Sandwich Theorem. And if we're going to use the Sandwich Theorem, our burden is to make these two things happen, and then we get this for free. So the function we care about is this function, but our job is to get this function trapped in between two other functions. So I'm just going to start fiddling around, and these two other functions are going to just kind of come out of thin air, and it's going to look like I'm just kind of magically doing this, and that's just because I have experience. So I'm going to start out with this fact. It certainly is true that the cosine of a number, that's a z, so the cosine of any number is in between -1 and 1. Because if you look at the graph of cosine, right, it oscillates up and down in between -1 and 1. So the cosine of any number is in between -1 and 1. So it's also true that the cosine of this number is in between 1 and -1. So cosine of any number is in between -1 and 1. So in particular, the cosine of this number is in between -1 and 1. Now I'm trying to get this function trapped in between two other functions, and I'm not quite there. I have this trapped between two other functions, but I don't have this whole thing trapped in between two other functions. But I've got a true statement, and if I multiply the same number in all three places here, I'll still have a true statement. So what I'm saying is I could multiply by 3 here, and multiply by 3 here, and multiply by 3 here, and then I'd still have a true statement. But instead, I'm going to multiply by x squared in all these places. So when I do that, I get the statement that negative x squared is less than or equal to x squared cosine of 1 over x squared is less than or equal to x squared. So I took this statement, which I knew was true, multiplied by x squared in all 3 locations, and now I have this statement. The reason I did all of that is because now I have the function I care about trapped in between 2 other functions. So I've met this burden right here. I've trapped the function I care about in between 2 other functions. Now the second step to verify is to see if the limit of the bottom function is equal to the limit of the top function. So I need to calculate the limit of this and the limit of that. So I'm going to calculate the limit as x goes to 0. Still happening, I apologize for this. The limit as x goes to 0 of negative x squared, and I'm also going to calculate the limit as x goes to 0 of x squared. And I'm really hoping that these will come out to the same number, right? Because if they do, then I've met this burden. Okay, so I'm going to try this one. Right now I have the limit of x squared, but there's a limit law that says that that's the same thing as the limit of x and then squared. So here I was powering first and then limiting, and there's a limit law that says I can limit first and then power instead. Okay, now so let's make a table in our head. This is the function y equals x. So whatever the x is, the y will be. So if I plug in 0.1, it'll spit out 0.1. If I plug in 0.01, it'll spit out 0.01. So that's getting close to 0. And then, of course, 0 squared is 0. So this limit is 0. Okay, now over here, that's like negative 1 times x squared, right? So I could take the limit of negative 1 times the limit of x squared, and I could use the power law. So I did 2 limit laws there. Limit of this times the limit of that, and then the power one. This limit is 0, right? Just did it over there. This function always spits out negative 1. So if I plug in 0.1, it spits out negative 1. If I plug in 0.01, it spits out negative 1. So those are getting close to negative 1. 0 squared is 0. 0 times negative 1 is 0. So that's good news, because these limits are equal to each other.
Good afternoon, Lebanon High School. Department chair meeting will start in 1 minute. Thank you.
So now I've met both burdens of truth. Both burdens for the proof. I've trapped my function in between 2 other functions. And I've also calculated the limit of this one and the limit of that one, and they were equal. And so what that means is the limit of the middle one is also 0. This could have been 7, but in this case it was 0. And so now I know the answer to this question. So therefore, 3 dots mean therefore. Therefore, the limit as x goes to 0 of x squared times cosine of 1 over x squared is also 0. So I never calculated this limit. I just calculated 2 other limits, and I knew that this limit was 0 from the Sandwich Theorem. All right, thank you very much for your patience. Hopefully I'll be back soon. Just keep doing your best until then.